Hello, everyone. I'm here today with Guillaume Gardet from ARM to talk to you about how we are envisioning an artificial intelligence ecosystem that can help people with their ongoing work, and specifically data scientists. So my name is Marco Varlese. I'm the architect on developer technologies and artificial intelligence here at SUSE. And as I said, we're here with Guillaume Gardet from ARM to talk to you about how we can raise green in this artificial intelligence race. So without further ado, I would like to introduce you to the concept and how we are actually envisioning it here in SUSE, which basically is based on three steps: the accelerate, the adapt, and inject. So if we start from the beginning, the accelerate piece, well, if you think about what artificial intelligence is, well, it's nothing more at the very core of it, at the very basics, than compute mathematical models using large chunks of pre-organized data set. So it is really necessary that your hardware is very well suited to offer the maximum compute capability, and that your software, obviously, starting from the operating system, can leverage those capabilities. Without going into too many details, we may really consider this as the first foundational step. And when we start thinking about software and hardware, they must obviously go together. So we have a variety today of different type of hardwares. We go from CPUs to GPUs to ASICs and FPGA. So what are all these really about? Well, first of all, it is important to make an important statement that modern CPUs today are already very powerful, and they shall not be underestimated, favoring at all cost, all the time, an acceleration path on the system. So yes, sometimes it is required for the boost, for the extra performance which can be given by the GPU, by the FPGAs, by the new neural network type of devices, but that's not necessarily always true. So in this case, for example, when we speak about GPUs, they are designed mainly to offload simple operation from the CPU. They offer high parallel operation, which is highly advantageous when we consider some specific type of processing. For example, when you imagine to process an image composed by millions of pixels, the GPU that can offer thousands of cores and it's designed to basically efficiently go through those millions of pixels in a parallel way, it will offer obviously a big gain in terms of performance. And at the same time, when we think about machine learning and deep learning specifically, those mathematical models which can get really, really complex, they will obviously take a huge advantage from the capability of GPU executing them. The FPGAs, on the other side, they consist of internal hardware blocks which can be user programmable, but they're not as flexible as the GPU counterparts are. And similarly, the ASICs, which at the very end, they are really specific type of hardware, which are firmware programmed, and they always do a specific type of task. So all in all, what we are really talking about here is a really heterogeneous type of ecosystem. And this is really what the requirement is all about. It's fantastic to have such a variety of hardware that we can leverage, but it's always also very important to be very cautious about what the requirements are to always pick the right ones. So how the next phase then looks like, the adapt phase. I've been talking about the hardware and all the greatness around that, but as I said, the operating system, the software and the hardware needs to really go hand in hand, because the the journey is quite long and it's quite complex. So when we think about the OS, the operating system, which needs to leverage and needs to enable all these different type of hardwares, what are we expecting? Well, we are expecting the ease of configurability. That's to reduce at the very bare minimum the time to implement the playground that we are going to look in a few minutes and focus immediately on the actual data. It must be reproducible, because when it's time to move from the prototype to the validation environment, so where things really happen, and then eventually to the production environment, it will not be required to redesign everything from scratch. Finally, it must be scalable. If the workload required more compute power, then it should be possible to grow the infrastructure dynamically and reduce that infrastructure when not longer required. The usual scale up, scale out. And there are a few assumptions to make to excuse the above explanation, obviously. So the development usually starts locally. Possibly a data scientist works on a laptop or on a desktop. Then quite rapidly that code gets migrated to a more powerful host, which could be, for instance, a cluster, maybe on premises. And suddenly a complex cloud environment now runs the whole model which we previously developed. So it's quite important to make sure that we can offer, and that people can embrace an ecosystem that can provide the scalability and grow from a desktop to a huge data center where things run in parallel on huge systems. An example of that in terms of software is represented by Kubeflow, which is able to manage all these complex pipelines in a very efficient manner, in a very simple, portable, and scalable way. However, when we think about Kubeflow, well, Kubeflow is not still enough. Kubeflow needs to run on a platform which is based on Kubernetes, and many times data scientists actually face things like huge data sets. So a lot of data that needs to be consumed. And this is where things, for example, like our cloud application platform can be of help, or our enterprise storage solution can be of help. So next, as I said, we had three phases: the accelerate, the adapt. Now it's time to inject. Well, eventually, when all these ecosystem, when the hardware is enabled, when the OS is ready, and when all the tools, frameworks, libraries are there for consumption, well, what we really want is to extend our platform with the AI capabilities. This is what we would really love to offer. And this means creating a platform which is self-healing, based on circumstances, that can basically adapt to the situations by learning and by adapting through machine learning, which basically means predict future potential failures. So how do we actually get at the end of this journey? Well, we have what we call different waves. The Ketchup phase, which initially is wave one, it's basically represented by us offering artificial intelligence packages, which are our foundational building blocks for our distributions. And this means offering machine learning, deep learning frameworks, offering pipeline management systems such as Kubeflow on top of Kubernetes, offering the development languages ecosystem and environments that data scientists are expecting to be in place, such as Python or R. And finally, as I said at the beginning, the operating system needs to be ready, needs to be able to leverage those complex hardwares that we are given. And this means working with ARM, working with NVIDIA, with Intel, with AMD, all the different providers that all different hardware vendors that can enable our platform. The next sub-phase, or still in the wave one, is represented by offering virtual machines for data scientists, containers, and eventually a full AI stack. This basically means being able to offer specialized AI containers, offer specialized custom virtual machines that can be, for example, running on Microsoft Hyper-V as well as KVM or VMware. And last but not least, we are seriously considering WSL as yet another enabler for data scientists to use and see our product. Finally, the surpass phase, the wave, is basically represented by plugins that we are thinking to add to our products, such as security threat plugins or predictive analytics and predictive scaling. Finally, the last step, the last wave, is represented by the predictive analytics engines, which we're thinking to basically offer on products such as the storage solution or the SUMAP product, or yet the cloud application platform. So how does it look like when we speak about all these, the actual architecture? Well, when we think about the architecture of the playground, where we basically just focus on the data scientist, on the developer, we're basically considering all the major tools, frameworks that today are being used by data scientists. And those are Python, Torch, the TensorFlow, ONNX, ArmNN, Keras, Caffe, basically everything that the data scientist would expect to use during his daily job. And as I said, the foundational building blocks of our offering is represented by the RPMs, by our packagings. Those RPMs are not just used or leveraged for the bare metal distribution, but they actually can be fed into the building of containers, of virtual machines, and finally, very soon, for WSL, which basically means that the overall lifecycle management is very much simplified, and the entry point is still always the RPM as such. As I said very briefly earlier, the virtual machines that we are going to provide, that we are already providing actually, are available on hypervisors such as VMware, KVM, Zen, and last but not least also for Microsoft Hyper-V. And they are actually targeted to various different distributions right now. They are available for our rolling release, Tumbleweed. They're available for our more stable release, OpenSUSE Leap 15.2, and last but not least, SLES 15.2. The only note here is that this package offering for SLES 15.2 is available through the Package Hub repositories. Now, what I would like to do is to also talk to you about how the playground picture is set aside together with the needs of an operator. They have very different needs. The data scientist has obviously a look on how to develop a new model and make sure that the model can be validated and actually works. The operator, the AI operator, will most likely focus mostly on deploying things to production, managing a very complex environment in the data center, and making sure that that ecosystem, that environment can be offered at scale to multiple data scientists, to multiple users. So when we look into that, the picture shifts a little bit to the left and leaves space for more tools, frameworks, libraries. And here we find things such as TensorFlow Extended, which is really becoming more and more popular when things get really serious and from development needs to be moved to production. And TFX has only one hard requirement, which is on Apache Beam. Apache Beam basically provides the facility for pipeline redistribution and management. And Beam can work on a variety of different other frameworks. We chose Apache Spark to be the one. And these are really like the three other core blocks that we envision. Then we have an optional part, which is represented by Kubeflow and Airflow, which obviously have with them, they're bringing with them other dependencies, specifically a Kubernetes, for example, distribution, or CASP in the enterprise world, and can also be leveraged on the HPC side when things need to be really run at scale. And again, all these can run either on OpenSUSE and SLE as operating system. And the last piece that we should really consider is when a huge data set, a lot of data is into the game. Imagine like what happens with the automotive industry, the machine learning there. We're talking about really petabytes, exabytes of data. Then you need a storage solution. This is really represented by SES in our case. And all that, as I stressed at the very beginning, needs to really run on a variety of different hardware and enable a variety of different hardware represented by ARM, by NVIDIA, by AMD, and by Intel. And with that, I would really like to pass the presentation to Guillaume, who is going to explain a little bit more about the ARM ecosystem and what we are doing in that regard. So Guillaume, please. Thank you.
So I'm Guillaume from ARM. I'm a dedicated engineer to SUSE and OpenSUSE so that we can work as partner. And I will show you some ARM-specific solutions for AI ML. So for ARM targets, we'll cover usual AI ML frameworks. I will have a little word about NVIDIA CUDA on ARM, and I will spend a little bit more time on ArmNN. So most AI ML frameworks which are available on x86 are also available on ARM. So we have currently TensorFlow 2.1, 1.15.2, PyTorch, Theano, 1NX, and Caffe on SUSE and OpenSUSE. We also have TensorFlow 2 container, and also virtual machine dedicated to machine learning. But you probably want to boost performances by using all your hardware. So you need hardware accelerators, probably, maybe GPU, NPU, or even FPGA. Or you can just get speed improvements on your CPU. That's why you are probably interested in CUDA and ArmNN. CUDA on ARM is only a technology preview for now. It's not really ready for production yet, but it's coming very soon. So CUDA on ARM will include the CUDA toolkit itself, but also the NVIDIA CUDA Deep Neural Network Library, which is also called CUDNN. It includes as well NVIDIA Collective Communication Library, NCCL. And if you want more details or download the packages, you can go to the link developer.nvidia.com/CUDA toolkit/ARM. Currently, there are some caveats. RPM packages for SUSE are still missing from NVIDIA webpage, but it should be fixed rather soon. And there are also hardware limitations for ARM because you cannot use CUDA on all ARM platforms for now. But SUSE demoed CUDA on ARM last year at Supercompute 19 on a dual ThunderX2 workstation with NVIDIA Tesla V100 on SLE15 SP1. So things are working already, but you need to wait a little bit for production. We can also talk about ArmNN. ArmNN is an AI ML SDK, but for inference only. It's a key component of machine learning platform. You can have a look on mlplatform.org, which basically groups some software initiative about AI ML. ArmNN try to bridge the gap between existing neural network frameworks and the underlying IP. It currently supports few models, so you can run ArmNN models, of course, but also TensorFlow, TensorFlow Lite, Caffe, and ONNX models. It's already deployed in multiple production devices, mainly on mobile phone with Android, but still it's deployed and work great. It's released under MIT license and developed publicly, and sources are on GitHub if you want to have a look. It's on github.com/armsoftware/ArmNN. So ArmNN is between your hardware at the bottom with CPU, a GPU, or an NPU, and on the top you have all the AI ML application, algorithms, and frameworks. And ArmNN is here to link your models and run it on top of your hardware efficiently. The workflow with ArmNN is the following. It's pretty common. First, you need a model, so you need to train your model. ArmNN cannot do that, so you still need to do it with TensorFlow or your usual frameworks, or you can also use a pre-trained model. So basically, for example, image recognition, you have training data with some images, for example, for animals, and you train your model on big powerful server in data center in the cloud, and you get a model. Optionally, you can convert this model to ArmNN format, or you can just use the TensorFlow or Caffe format. It doesn't matter much. There is no performance impact. Once you have your model, you can run it with ArmNN on your IoT or edge devices, which have limited compute power. So you give a new input, a new image of a cat, for example, and you run it on your model with ArmNN, and you get a result. ArmNN has different backends, which are hardware support, which are optimized to speed up your model by making use of most of hardware capabilities. So the first backend is CPU ref, which is just a C++ reference with no optimization, which is slow, so you don't want to use it. You have CPU hack, which is a backend acceleration for ARM CPU, which is very, very fast. Then you have the GPU hack, which will use OpenCL acceleration on Mali GPU or any OpenCL 2.0 GPU. It's also very fast. And then you have supports for pluggable backends. So you can create your own backend for your own accelerator. Could be an NPU, a FPGA, a DSP, etc. So maybe your hardware vendor can provide some backends for ArmNN as well. Here is why you should use ArmNN instead of just your TensorFlow or Caffe or whatever. It's because it improves your performance. On these graphics, you have some comparison on few models. So ResNet 50, MobileNet, Inception V3, which are run with ArmNN on little CPU. Here it's Cortex A55, It's also run on big CPU with Cortex A76 and also on Mali GPU with Mali G71. So you can see that the improvement can vary, but overall it's an improvement between 3 and 5 x faster. So it's good to use ArmNN to improve your performance. Here are some data about the performance on face unlock. So when you take your mobile phone, you can probably unlock it with your face. So here is how long it takes to perform it. On the left side, you have some hardware which run more than 10 seconds to get the face unlock result. And on the right, it's under 10 milliseconds. So the scale is a log scale. So on the left, you have, for example, the Cortex A53, MP4. MP4 means 4 cores. So this is basically a Raspberry Pi 3. You can see it's not very powerful. But if you go on the center, you have the first GPU with Mali G52. And then you also have more on the right Neoverse N1, which is the new Cortex, the new ARM Neoverse from ARM, which is very powerful. It's based on ARMvi.2. And then you have NPU with Ethos N series, and also a powerful GPU with Mali G77 with 12 cores. So depending on your needs, you can run on a slow CPU, or maybe on a faster CPU, or maybe you can jump on a GPU or an NPU. It really depends on your needs. What about ArmNN in SUSE and OpenSUSE? In OpenSUSE, you have a package for ArmNN in Tumbleweed and also in lib15.2, which is full-featured, which means all backends are supported and all models are supported. So all models includes ArmNN, TensorFlow, TensorFlow Lite, Caffe, and ONNX. On the SUSE side, it's available through PackageHub, and it's also full-featured. So all models on all backends. If you are interested, it's developed at Science Machine Learning projects on OBS. And you also have some interesting details on the OpenSUSE wiki. It's on en.opensuse.org/ArmNN. And you have, for example, how to run examples, samples, etc. Now I will show you a little demo on the HiKey 960. It's a board with 4 ARM Cortex A73 and 4 Cortex A53. It also features a Mali G71 MP8. So it's tiny, but it's quite powerful. The purpose of the demo is live handwritten digits recognition using a model which is pre-trained against the MNIST dataset with TensorFlow. So let's connect to the board via SSH. With CL info, you can check the platform and device name, which is a Mali G71. Now, in the demo program, you can either use CPU accelerated, which is the first case. Here is the demo, so we can draw a 0 and it's detected as a 0. You can check with a 1. It's detected as a 1. Now 4. It's detected as a 4. The same with number 3. Now stop the program and use GPU accelerated instead of CPU. So now it will use OpenCL. Can try again with a 0. Predict. Again, it's detected as a 0. 1 is detected as a 1. Number 4 detected as a 4. And the same with number 3. Thanks for watching the demo and the presentation. If you have questions, please ask through SUSECON website, and we will try to answer them. Marco, if you want to add something?
Thank you very much for listening to us. I hope that you really enjoyed our presentation here today. I wish you a very pleasant SUSECON Digital overall, and please reach out to us. We'll be available to answer your questions on the platform. So thank you again, and talk to you soon. Bye.
Thank you. Bye.